last time I introduced electrical discharges and glow plasmas effectively, and some of the things that they might be able to do. But then we should have a look and see what they look like in a lab environment. And I've got a few toys for you to see. We looked at my plasma globe last time, but this time we shall look at a few other things at air pressure and see what happens, investigate them, or think about how they could possibly come about. Then we'll talk about what's happening in the plasma and we'll wrap it up for today.
Welcome to my lab. This is me over here. Oops. Hello. Now I'm going to turn you back to over in a neutral direction to have a nice neutral background so that I can show you this. It's a lighter, and we will see the arc from this lighter. It's one of those plasma lighters. Let's do it that way around. I can get it better angled to the screen. There it is. And what you can see, it's a little bit out of focus. Let's try it over there. It's a little bit out of focus, but you can see a purple spark. It looks a lot duller to me than it does to you. It's probably got auto brightness up a little bit. Okay, now let's have a look at some of my other toys that use electric sparks. This one is my electric banana. It's actually a stun gun inside a banana fruit case, but I want it for the spark. So there's my spark bit, there's my hand, and I'm going to pull this trigger and you can see the spark. Look at the colour. It makes this camera go bad. Look. It smells very strongly of ozone, and it's overloading my camera. I'm going to turn the camera down and see what happens. So now we've got it low light. Let's go back to the last one and see if there's a difference. So that's a different spark, same lighting. This one appears to be purple, the other one appears to be quite bluish. Although it's more purple than it appears to be to me. It appears quite white to me. So this is, oops, I'm just checking. This is what's called a Jacob's ladder. It's 2 copper wires and a high frequency circuit. And I'm going to apply a voltage across them. So it will look like this. It will strike an arc, and then the hot plasma in the arc, which we will deal with later, as a theme, the hot plasma in the arc will obviously rise because it's hot, and that will cause the arc usually to go up. Sometimes it gets stuck. Ooh, it went up there. And there it is, going up. You can see some of the time it's purple and some of the time it's comparatively white. You can see the ends are purple and the middle is more orangey. Right, I'm going to stop and turn the brightness down, effectively turn the gain down, and just run it again to see if there's anything different you can see like that.
Okay, so this is a Tesla coil. No, it's not. It's a little Tesla tower, I guess. And I'm bringing up a small an earth lead. You can see the sparks going from the earth lead. The sound is off in this one, and I'm in a disembodied state in the corner because it interfered with the microphone of the camera. You can see it's relatively dark, that's why the picture's all grainy. So I've got the light brightness down because it's not a very bright spark. What you can see, okay, I've turned the brightness down even further. So now I've turned the gain off on the camera, sorry, so that we can see the spark better. And we'll see what happens then. Maybe it will change the color a little bit. It's taking me a little while to do this. This little high frequency, there we go. And you can see here that this is comparatively blue. So we've got bluish white color in some of these sparks, and we've got very purplish color in others. and that is dependent upon, slightly upon what we do with the camera. So it's the amount of brightness, should tell us something. And it's also partly to do with the frequency or the type of spark that we've got. I'm going to turn this off now. Oops. So here is my plasma globe again. What we can see is, oh, there I put my finger on it. What we can see is a low pressure discharge. There's a purpley pink color on one end, or there's a pinkish color on one end, and in between there's a bluish purple color, which seems reminiscent of the colors that we see in the air, but there's not air inside this globe. There is a mixture of gases, mostly not air, and this discharge is slightly different because the pressure inside the globe is lower than atmospheric pressure, which is why it can form lots of them, where we saw a single arc, a single spark forming in most of the other demonstrations that I had. The crossed purple ones are actually not at the same time. They go in one direction and then in the other direction, but it's doing it very fast at a high frequency, so we can't see it. It appears to be crossed sparks, but it's not really. So this is another type of plasma. It's a low pressure neon plasma in a bigger tube, and what we can see is the plasma is filling the whole of the tube because there is less outside pressure confining it. The ions can travel further, the electrons can travel further, and so they tend to hit more things and ignite the whole tube, and it's bent around in a curve outside the region that we can see. It's neon, so its emission band or the emission colors are red. Somebody's on the phone, so I'll have to go and do that. Okay, we're back. I'm a little bit weird disembodied head, but never mind, we'll try this method. So we have in our air, let's choose these three gases: nitrogen, oxygen, and chlorine. You check that my sound is on. Yep. So we've got nitrogen, oxygen, and chlorine. We've got our circuit, we've got low pressure, and we're going to imagine what happens when they get excited. So we're going to apply a high voltage of some sort, and some electrons will try to travel through the gas, and they will whack into these things. What will happen? Well, if we have these three gases, the oxygen will tend to take up electrons because it's electronegative, so it will tend to become negatively charged, and because it's a double bond, it'll be comparatively difficult to break it. We can break one of the bonds, so we can excite this electron into an antibonding state and break the bond. We can capture an electron and make a negatively charged species, but it will be comparatively difficult to break it, although not super difficult. If we take the chlorine, it's only bonded by a single bond, and it's in a relatively high energy. The excitation of this into its antibonding state uses only visible light. We know oxygen and nitrogen don't break any bonds with visible light. That's why we can see through them. That's why they appear to be colorless. I'm sorry about the shadow on my head. I wonder if there's a way of dealing with that if I sit a little bit further away. So so oxygen and nitrogen don't absorb visible light, and they don't break any bonds. Chlorine does. That's why it appears to be green, and it's why it becomes very reactive in the light. It can break and form a chlorine atom, two chlorine atoms, one of which will be charged. Maybe it's quite difficult to get them positively charged. They're likely to stay negatively charged, but still we can make the chlorine into atoms relatively easily. Sorry, phone's ringing, let me deal with that. Unfortunately, I lost the audio for this part, so we'll have to do it with a voiceover, so my lips are not going to match. What I'm saying here is that we're imagining a case where we've got low pressure, we've put one of the electrodes to earth, and we're applying a voltage, and we would expect to see some kind of voltage drop between the two electrodes because it's a gas, it's not going to conduct. So we're going to get a basically fairly constant level of voltage drop between the two electrodes. That's because the gas is the non-conducting part, and all of the rest is way more conducting, so nothing else is going to happen. We're not drawing very much current, or probably not any. Any stray electrons will go to the positive electrode, but otherwise nothing will happen. Then what we're going to do is we're going to turn it up a bit, and it will light a plasma, in which case the gas in between will suddenly start to conduct because the electrons can move. And that's way more conductive than a normal air is, and so therefore the conductivity will go up, which means that some parts of the gas will then have a lower voltage loss, voltage drop per unit area. Current will flow. If it's a low power supply, as I mentioned before, the voltage will drop, and then it will the spark will go out. But what happens if it's a lower pressure and we can keep it going, we can maintain the plasma? So now close to the electrodes there will be less ions because they can go and hit the side. If it's a positive electrode, it will push away electrons. It will pull in electrons. If it's the negative electrode, it will push them away. So near the electrodes there will be a much bigger voltage drop than there will be in the middle, where the plasma is quite conductive. So here I am trying to draw that. So there we are in the middle. There's pretty much no voltage drop because the plasma is conductive, but near the ends, because the plasma is not so dense, it's got less electrons or ions in it, there's a bigger voltage drop. And this explains then why the plasma behaves differently close to the electrodes and far away from the electrodes. There are really two main reasons. Close to the electrodes there's a higher energy drop per unit distance, and so there is more energy in the plasma, there's more excitation, so the ions are going faster, they hit things harder, and so if we have a mixture of gases like in the plasma ball, in the plasma globe, at the ends of the plasma there's more energy, so more gases are excited, and if we get one that is brighter, then that one will appear. So that's why the pink color appears on the ends. In the middle, we can't see it. We see a lower energy band, which is another gas in the middle. The other thing that can happen is we can knock things off the surface. So that was what was happening on my Jacob's ladder, probably, that dirt on the wires or maybe some copper out of the wire gets knocked out, and that's what causes the orange color, probably fat, but possibly copper being knocked out into the end of the arc, and the middle of the arc is behaving normally. So we excite different species and we have different effects. This can be useful to us because we can have more effect near the surface where we want it to be. It can also be annoying because our plasma is conducting, so it's hard to generate a voltage difference inside the plasma. We can only generate it near the end. Now considering the other extreme, where we have a plasma that ignites and strikes an arc from here to here. So we start increasing the voltage, increasing the voltage, increasing the voltage. This would be like the stun gun. We get suddenly enough voltage for some electrons to be freed from somewhere, and they travel across the plasma. So we light the plasma, we make some electrons in here. Let's make them little green dots, and the little green dots are going to go out, but mostly towards the positive electrode. They're going to go slightly towards everything else because electrons have a low mass and they have very high velocity because they've got the same energy, and because they weigh a lot less, they are going a lot faster. And then we have some atoms or some ions, and they are going to travel towards the negative electrode, probably. But we already had an example where the ions are typically, oxygen and chlorine ions are typically negatively charged, so we can't keep it as a constant, but in many cases it's an atom or molecule with missing electrons and positive and electrons. So here we are. So here we are with our ions moving, and they're moving a lot slower because they weigh much more than the electrons. The electrons are moving incredibly fast and they all leave, so it means that the plasma becomes biased effectively. The plasma becomes positively charged and everything around it becomes negatively charged because the electrons rush into them. So if we have a piece of sample here, whatever we're going to treat, it will first of all get hit by a whole load of electrons. It will then get negatively charged if it's not attached to Earth, and then it will attract these positive ions towards it. If it's attached to Earth, then the actual plasma will become positively charged compared to Earth, which is effectively the same. We get a charge difference, and that will cause the ions to be accelerated towards things, also things that we're not deliberately putting at a potential. So taking this from a perspective of each gas, if we take the nitrogen, or all of the gases can become excited and become the excited state where it's got some excess energy. The electrons are in a raised energy state, or maybe there's a vibration, and so we denote that with a star. It's typically an excited electron. So we can excite the nitrogen to nitrogen star. It's just excited. We could excite it to an ion, and we could maybe break one of the bonds, and we can go all the way. We can make all kinds of species up to a nitrogen atom with a positive charge, maybe 2. If we take the oxygen, as we said before, the oxygen is more likely to become negatively charged, and if we break some of the bonds, we can make more energetic oxygen, and we can make oxygen anions. But we can also make the thing that we fear. We can make ozone if the pressure is high enough that the oxygen can meet another oxygen molecule, because it takes more than one oxygen molecule to make ozone. We need O3, so we need it to react. That was what I was going to look up, but never mind. I was going to do the maths and remind myself which way round the charges are on the ozone, but never mind. We can make ozone. It happens mostly at higher pressure, which is why I could smell it in the lab at atmospheric pressure. In low pressure, the probability of meeting another oxygen before it hits the side is quite low, and so it doesn't make as much. If we have chlorine, we tend to make chlorine ions, and this whole pathway and all of the possibilities shows us that we can get different colors, because if we increase the energy, we can excite more states. And if we reduce the pressure, we shift how the molecules interact with each other, how long they move before they hit something else, how much energy they can take from the power supply before they hit something. If we have nitrogen and we have it at low pressure and we put more and more energy in it, we get different species. We end up with the nitrogen atoms on their own, and that has different color. They emit a different color of light than nitrogen molecules do. And likewise, the oxygen also has different things that it can do. The different emission spectra of oxygen are slightly different, and that's why we see different colors with those different things, because at a low frequency, effectively at DC, we can get a lot more power into the plasma constantly. When we strike the arc, it takes a very high power, but only for a short time, because the power supply usually breaks down. If we have a high frequency plasma, it tends to excite more gas, but to a lower energy, and so we get a different color. In different pressures, we get different colors because the gases interact with each other more, and so on. So that was an introduction to plasma. We will be thinking about how it can interact with surfaces, because that's the whole point of our subject. But now we know what a plasma is, how we make it, what it looks like. So that was the more practical part of plasmas for us.